Hello and welcome to Explaining Rust Analyzer, a series where we try to understand how Rust Analyzer works, one subsystem at a time. Last time we looked at the analysis host and virtual file system, two things in Rust Analyzer which actually store the state and implement this ID-specific thing of maintaining state which evolves over time as a series of consistent snapshots. Today we will look at the Rust Analyzer main loop, the place where we actually plug this state into a real-world program which does input-output and which actually causes this state to evolve and uses the state to compute various useful features for an editor. So without further ado, let's open our code. The crate which we will be looking at today is called Rust Analyzer. The reason for this name is that this crate actually produces the binary, which you know as Rust Analyzer, basically just to make Cargo's default conventions work. It would probably be better to name this something like language server or something like this, because Rust Analyzer really, at least I imagine it to be bigger than just language server. It is more about providing a library for analyzing Rust code, at least eventually, I don't know, 10 years down the line. But today, the LSP server is the main use case. The crate is pretty big. It probably is one of the most complicated bits of Rust Analyzer because it has to, because it has to orchestrate state, and state is the most complicated bit in programming. Internally, it organized is a typical Rust binary. There is a libtors crate which contains all the stuff, and there is a much smaller bean crate which contains the actual main function and all that stuff. So let's start reading the code starting from the main function. I will be glossing over a lot of bits of Rust Analyzer crate today. I want to cover only like the happy path of the main loop. We will probably record some extra things to deal with other stuff. For example, the first block you see here has to do with expanding procedural macros, because we want to run procedural macros in another process, and this thing actually implements the host process for those procedural macros, but we won't cover in this today. Finally, there is the actual main function here. We start with parsing command line arguments. Then there is this magical bit of code, which I'm not sure how exactly works, but basically people who do debug Rust Analyzer use this to attach to Rust Analyzer at the moment it starts. Then we do some login setup, and finally we go to selecting a specific command and running it. So Rust Analyzer binary supports a bunch of commands. The main one is, of course, the LSP server, the one we will be looking at, but there is also a couple of commands for batch analysis. If you remember, on the first lecture, I said that there is Rust Analyzer analysis start commands, which type checks the crate in the batch mode, and we use this to, for example, check how fast a certain optimization makes Rust Analyzer. But you typically don't use it. The main case is this LSP server command. Again, we do a couple of special things here, and finally we actually run the server. So this is a function run server where the LSP proper starts. First, we create an LSP connection. LSP is a rather simple protocol. I suck at OSI model, so let's say it like this. The messages are exchanged over standard input and output. The messages are in the JSON RPC 2.0 format, which specifies like the envelope for messages and the overall request response cycle. and the actual messages are dictated by the LSP protocol. So the connection object is, well, the connection between the server and the client. When we create connection over a standard I/O, we get back, first of all, a pair of channels for receiving and sending messages, and channels here are cross-beam channels. Actually, this interface is really bad. Well, it's not really bad, but it's definitely suboptimal. Usually, you don't want to make channels a part of your public API because that forces you to use a particular implementation of a channel. A better architecture is usually to accept a callback. If you accept a callback, then the user can provide a callback to send over any kind of channel they have. If you fix a specific channel one, then the channel is fixed. But that's probably not important. Anyway, so we get back this pair of channels to communicate with server and client, and the channels actually don't expose the underlying details of how the messages get sent over the wire. And in particular, this library also, I believe, supports socket connection. Yeah, not only STD-IO, but we only use STD-IO. Anyway, the other thing it returns is it returns threads, and threads is just a pack of two join handles, which you should join at the end to make sure that there weren't any I/O errors during communication with the client. Okay, so once we have the connection, we do some handshaking procedure with the client. We also get initial configuration, and we use that initial configuration to initialize some stuff. So this bit about configuration is actually one which I will be aggressively skipping in this lecture. Actually, handling configuration and handling project setup is very complicated. The worst thing which can happen to the Rust analyzer is if you start typing in cargo toml, then we need to reload project model, and that is slow and horribly complicated. And a lot of code you will be seeing today actually deals with this problem of changing configuration while you are running. But we won't be covering it today because it's complicated. So now we think about the steady state, that we have some fixed configuration from the client, we have some fixed cargo toml, we already run cargo metadata, cargo check, and basically we only need to react to the user actually editing the code. So we just skip all this initialization and configuration stuff. Yeah, just a couple of words why this is complicated. This is complicated because you want to be able to change configuration on the fly. And the question, what happens if you know that the old configuration is already wrong, but the new configuration isn't ready, and you have to handle some user request right now, is very interesting. We won't cover it today. Okay, finally, after this initial handshake, we start the main loop of Rust Analyzer. And the reason why this is called the main loop is because very soon we will actually get to an actual loop which takes a message out of a connection and processes it. To run the loop, we first create a global state. Global state is a rather big data structure, probably the struct with the most amount of fields in Rust Analyzer. No, I think it's actually not like the biggest struct. I think completion context. Yeah, completion context is probably worse. Anyway, global state still has a fair number of fields. So the main field here is probably analysis host. This what stores the actual logical state of the set of Rust files. All the other fields here are state which is related to the protocol itself. For example, what is a request queue? The LSP protocol is based on messages and responses. If you actually take a look at the LSP types message, that will be helpful. So the LSP protocol is symmetric. After the connection is established, both the server and the client can send requests to each other. And they can send three kinds of messages. They can send requests, they can send responses to particular requests, and note that request return contains an ID, and response should contain this same ID, and there is a requirement that every request should get a responding response. And also there are notifications. Notifications are requests for which responses are not required. So you cannot, notification doesn't have an ID, so you cannot respond to notification. So yes, requests and responses. Processing requests can take some time, and there could be concurrent requests. So for example, a client can send you like 3 requests. You can start processing all 3 of them, and then you send 3 responses back. It's not like you have to finish processing the first request before starting processing the second request. So this stuff is concurrent, and generally you have a bunch of outgoing and incoming requests in flight. This request queue is what handles this state. So there is like this incoming and outgoing tables, and each table stores a mapping from the request ID to the corresponding data. It's a little bit like handwritten futures, maybe. Okay. So yeah, that was an example of auxiliary state which corresponds to protocol. Let's actually go right through every field of this struct and explain what it is. Okay, so sender. Sender is easy. Sender is the outgoing messages to the client. So when we send something over the sender, we get a message sent to VS Code. Request queue we've already covered. Task pool. Task pool is more or less a thread pool which stores the tasks which we spawn in background. So for example, when we do syntax highlighting in the background, the syntax highlighting is a task, and this task is stored in this task pool. Loader is the virtual file system loader we've seen a couple of lectures back. Config is configuration, like global configuration for the server. Analysis host is the thing we covered last time. This stores the actual Rust files and the rest of stuff. Diagnostics are not really important, just some temporary cache. Memdocs are important. As you recall, virtual file system generally watches the file system, but not every document exists on a file system. Specifically, when we type something in the editor, those changes are not immediately persisted to the disk. The editor maintains them in memory. So memdocs reflects the state of these currently not yet saved files which exist only in editor's memory. Again, this is another bit of cache. This is important. LSP protocol has initialization sequence and shutdown sequence, and shutdown sequence is actually more complicated than it needs to be for some not really good reason. So this flag helps us to track this shutdown sequence. Some more caches here, something not really important. This thing is interesting. This thing is another source of concurrency. So flight check is what we call the process which launches cargo check and background and processes cargo check messages to show you 100% correct diagnostics from compiler. As usual, running cargo check is slow, so we do this in a background concurrently to all the other things happening. And these flight check fields track that concurrent activity. In particular, this is kind of like a separate actor thing, and we can try to send and receive messages to it, although it doesn't really make sense that we store both and okay, yeah, it's okay. It's complicated. It will be covered in a separate lecture. The next bit of fields tracks the virtual file system state, and again, this is concurrent. So we need various bits of auxiliary state to track concurrency. In particular, if you recall, we create virtual file system from a specific configuration, and that configuration has a version, because we need to understand when virtual file system tells something to us, what config version was current at the moment where that event actually happened. Because that time where we get an event might not necessarily correspond to the time when the event was produced. We cannot look at the current configuration and use it to interpret the events. Finally, this group of fields is something which we are explicitly not covering. This is exactly for solving that problem of concurrently updating configuration on the fly. And as you can imagine, this huge document explains that, hey, that's actually a hard problem. And there is a couple of more caches in there. Okay, so to sum up, GlobalState stores the core state of rationalizer analysis host and also a bunch of auxiliary states for language server protocol, like a queue of ingoing and outgoing requests. Okay, let's go back to the main loop. The main loop starts with creating GlobalState, and this GlobalState, this is more or less just creating the data structure, although this also actually runs this task pool, which is internally a thread pool inside. So in rationalizer, we generally try to follow the structured concurrency paradigm, meaning that we want to make sure that every concurrent activity has its owner, and that by the time that the owner drops, the concurrent activity also ends. And GlobalState turns out to be the holder of a lot of concurrent activities. By the way, the name in GlobalState is, I really like this name. I struggled very long trying to come up with a reasonable name for this thing. I didn't succeed, but I've read source code of the Sorbet project, which is also an awesome thing to read about if you care about IDs. And in Sorbet, the similar thing is called GlobalState. So thank you, Sorbet, for giving an inspirational name here. Okay, so let's go back to main loop. Finally, after we create the GlobalState with all the thread pools, we call the run method. The run method, again, does some complicated setup which is relevant to this dynamic configuration loading. And finally, we get to the main loop. So this, like 7 lines of code, are the core of rationalizer. And as you see, they are pretty simple. Ideally, that should be just 1 line, but whatever. So what happens here? This is an actor, in some sense. We fetch a next event, and then we handle event, and then we continue to the next event ad infinitum until someone tells us to actually close the server, at which point we exit. Nothing particularly interesting. And that's actually why this thing is more complicated, or maybe not. Yeah, anyway, I've told you that LSP's shutdown sequence is slightly more complicated than it needs to be. That is because it has like 2 exit methods. It has exit request and exit notification, and actually one of them is extra, but anyway, that probably goes into the weeds. So yeah, to understand how rationalizer works, on the high level, you need to understand these two methods, next event and handle event. Next event describes everything which can happen to Rust analyzer. It selects several sources of concurrent events. The main source is the receiver of LSP messages. So this thing is what editor tells to us. Actually, let's see this in action. No, I don't want these settings. I want workspace settings, and I want to... Yes, I want to comment this one. So this setting, Rust Analyzer Trace Server Verbose, is hugely helpful. It will show you this thing. And these are actually the... let's open some smaller file so that let's open some smaller file such that the amount of output is actually smaller, so we can easily see it. I am mixing my hotkeys. And now if we type something here, we actually see that a bunch of activity happens. So first of all, the client sends us text document the change notification, and then it sends us in the hints request. And then we send semantic tokens refresh request, which kind of doesn't fully make sense. Again, that's a separate issue when we will be discussing syntax highlights specifically. There is a bunch of some kind of progress notification because everything takes time, so we want to track progress. And that doesn't really... Actually, look at this. I'm really unhappy that the amount of stuff that happens on small update is so big. I guess it makes sense to some extent, but I wonder if we can refactor it to make it much more frugal. Anyway, finally, here is like the interesting request where the client asks us to get the syntax highlight information, and it actually does this for many files, which again makes sense in some sense, but not in all the senses, and there's a bunch more progress. And finally, the results of syntax highlighting. So as you see, the protocol actually is pretty chatty. I guess I have some simple config somewhere, which I use when I want to make this less chatty. Let's see. No, doesn't really, yeah, anyway. Basically, what I'm trying to do is that you can do stuff like disable semantic highlighting to make, to reduce the amount of verbose messages. And somewhere I have a project where I have all those disabled, but I don't remember where I actually have this code. Okay, so let's get back to this event, next event. Yep, so this receiver is for messages that the client sends to us. And it is the first case in this select. The second receiver is our task pool. If you recall, task pool is the thread pool where we run background tasks. And one of the possible events is that background tasks complete. A background task completes. Then we get it here. Finally, virtual file system may say to us that some new files are on disk. And finally, cargo check, which we are running in background, might come back to us with a bunch of new diagnostics. Again, it's useful also to look at this event definition. Basically, this event is everything which can happen with Rust Analyzer. This one we saw today, it's really simple. This one we saw in the first lecture. This one we probably will cover today because it describes what kind of things, what kind of background jobs we spawn. But let's quickly look for this actually. Yeah, actually, this we don't cover because this is about that dynamic configuration changes. This we won't cover because they are not really important. And this is the main task. When the background LSP request is fully processed, we get a response as in a result, and that actually should be LSP server response, because I really like qualifying all my types. That way you immediately understand like what kind of thing it is, because like response doesn't tell you much. And let's actually fix this while we are at it. So response should die. Yes. As you see, I'm not actually using check on save functionality because it is slow. What I do is I use Rust Analyzer run functionality because it lets me to run cargo check on demand. But recently, for some time, it doesn't trigger every time in VS Code. I'm not sure what's the problem here. I haven't investigated it yet. Okay, so we fixed this. Well, let's go back to event. Yeah, so the main thing that the task has is a LSP server response to some previous message we got. And yeah, flight check we are not covering in this stuff. Okay. So using the select, we got the next event. And here is the heart of the Rust Analyzer, the actual processing of events. To remind, this is all happening inside the global state. And this method actually mutates the global state using this event. I really like this architecture with an explicit event handling loops. So if you think about something like an LSP server, your first idea would probably to put this event loop into the framework and let the caller to just register some kind of a callbacks. I don't really like it because what the main loop fundamentally does is that it changes the state. And it's if you do callbacks, it's hard to see how the state is threaded throughout the execution. So today we will see how the state evolves really closely. I guess the framework style callback-based architecture is great for stateless systems. But if you hand an event loop, there is a lot of benefits in being able to write this event loop yourself. And here is the first one. As you see, the first thing we do inside the handle event is that we call loop start, which we call instant now. And remember this as the start of a loop. And then at the end of the loop, we actually measure how long this particular event took. And then if it was longer than 100 milliseconds, we show an error. And ideal, we are not striving for it now because there are higher priority tasks. But what we will end up doing eventually is that we will end up guaranteeing that this loop never actually blocks and never takes more than 60 milliseconds time. Because again, this loop also processes all the typing of the user. And obviously, if you are spending 100 milliseconds to react to some virtual file system event or something like that, you cannot react to the user actually typing, which places the lower bound on the latency of every operation. So we really care that this doesn't block for too long and we enforce it. Right now, this sadly happens a lot during configuration changes, but generally doesn't happen during normal operation. Again, as I've said, configuration change is a huge can of worms. Yes, and I guess before we go further, I should mention that I forgot to explain one crucial thing. And the crucial thing is that the code here is a mess. I don't really like it. I would love to write it better, but I don't know how. And the reason why the code is a mess is that there's a lot of concurrency happening here. And I haven't yet found a great patterns to tackle this concurrency in a nice way. I do like the runtime behavior here, but the way it is expressed in code, I don't really like. I have some in progress Actorish library, which makes this better, but yeah, haven't actually tried using it yet. Anyway, so as you see, if you write this main loop yourself, you can easily do stuff like tracking the time. What else you can do? Well, you get a single place through which every event in the system goes. So this single log line basically tells you everything which happens with Rust-Liza, and that's extremely cool. Okay. Let's see how event handling works. So there's a block for each event. Before this block, we look at this quiescent variable. This is, again, a thing I'm not explicitly going to say about. Basically, Rust-Liza is in quiescent state if all the pending configuration changes are done. And if you are in a state where you are running cargo metadata because you have added new dependency to cargo toml, well, you are not quiescent, so you shouldn't be doing any complicated analysis. And let's start with virtual file system, because we already know events from this. The first thing to notice is that we have this loop pattern inside, where we handle the current task, and after we handle the task, we actually try to fetch the next task of the same kind. Try receive on crossbeam channel yields the next task if it is already in the channel, if the channel wouldn't block while receiving this task. This allows us to coalesce several virtual file system changes into a single update. And this pattern is used for many other events as well. So progress is not really interesting. They won't be looking here. Well, it's interesting because this is a big architectural constraint on the system that you want to be able to report how far it got ahead in the current operation, but it's not crucial, so we won't be covering it in this lecture. Also, it's not really well done. Probably we will refactor it later, and then it would be something worth covering. Okay, so the primary message we get from virtual file system is that a bunch of files has changed. If we see this, when we try to modify the contents of these files in virtual file system, and again observe this mutability and Actorish fit into the architecture, we detect changes to the files and we read the contents of a file on some other thread. However, we actually update the current view of the world on the main thread. And one interesting wrinkle here is that if this updated file is actually not saved on disk, if its state is managed by the editor, we do not update the view of the file in the VFS. If you remember, VFS and loader has this invalidate request, which we were talking about a while ago. So this is exactly why you need this invalidate. When you don't update the VFS file because it is managed by the editor, when the file actually is saved on disk and no longer managed by the editor, you need to invalidate it and to ask VFS to refetch the contents from the file. Okay. As you remember, set file contents updates the contents of the VFS in place, and it also records the fact that there is some change to the VFS. Because we process these events in bulk, we are able to accumulate several changes. And again, this is an example of pattern which is hard to understand, hard to do in a system where you just register callbacks, while when you do the main loop yourself, you can easily decide which events need this kind of batching and which events don't. Okay, so we processed this bunch of events and go to the process changes. So here we only accumulated stuff which have changed. In the process changes, we actually apply the changes to the underlying analysis host. So we start with this change struct, which we see last time. And then we take the changes from the virtual file system. If there are no changes, in fact, then we quickly return and do not return true. So we say that the state is unchanged. However, if there are some changes, we plug them to the change. So this one is the most important. We set the contents of a file. And then we apply the changes to the analysis host. And finally, the change could have actually invalidated our config. So we call maybe refresh method, which is horribly complicated and which deals with dynamic configuration. So back to the main loop. If we see that the state is changed, we update file notifications in the thread pool. What's a horrible name? Yeah, basically, most of the things in LSP are pool-based. The editor asks us some query. The only exception to this model are diagnostics. Diagnostics are push-based. When the server notices a new diagnostics, it should push the diagnostic to the client. And when the server can notice a new diagnostic, well, when some change was made to the state, and this is exactly what happens. So if we go here, we see that again, this is not interesting and we're ignoring this. But this is interesting. So if the state was changed and we are not in the process of changing configuration, we collect all the files which are currently visible in the editor. And again, this is actually buggy because what memory documents tells you is which files are managed by the client, which files are not saved on disk. It doesn't tell you about which files are currently visible because, well, LSP doesn't really have this concept of visible file. So you cannot easily push diagnostics only for interesting files. And usually for giant projects, you don't want to push diagnostics for everything because computing diagnostics for everything actually takes a long amount of time. Basically, computing diagnostics for the open file is a constant operation because, well, the size of you only have the size of visible files. The size of visible files is roughly constant. You don't usually have gigantic files. So the amount of diagnostics we have is also constant. And recomputing that, well, in pathological cases, it can be a lot, but usually it's not. However, if you want to push diagnostics for the whole project, well, the whole project is unbounded. It might be millions of lines of code, and that scales badly. I do think that if implemented properly and optimized correctly, it shouldn't be a problem to compute diagnostics on the flight for like large projects, but not for really huge projects. And I do want to have an architecture which scales to huge projects. That's why we try to do this optimization and send diagnostics only for visible docs. By the way, we call this subscriptions. We kind of like fake it that the client subscribed to diagnostics to this file. And the idea of subscriptions goes from comes from, okay, let me Google it. Yes, the idea of subscriptions comes from the Dart analysis server protocol, or I don't really recall how it is called, but basically this is LSP for Dart, which predates LSP by Microsoft. And at least in my opinion, this LSP is actually better. In particular, it doesn't have this ambiguity problem between visible files and unsaved files. It also deals better with changes and consistency, which we will see in a moment. Anyway, we take these subscriptions and then we spawn a background task to publish diagnostics for each of those subscriptions. Okay, let's go back in the call stack. The important idea here is that we have this main loop, and in the main loop first we try to eagerly apply many updates, many changes on the file system, and then we try to react to all of them. Again, this is something which is easier to code up when you write the main loop yourself, because it's not like you update to every event in isolation. You actually want to update to a batch of events and then process the changes for this batch once. And yeah, then again, a bunch of stuff which relates to configuration changes, and finally this diagnostics about how long the loop took. Okay, so this was about virtual file system. We started with virtual file system because this is the source of changes, the source of events, how the data gets into Rust Analyzer. The second source of events and data are LSP protocol notifications. In particular, when you type something in the file, it is the did change text document notification, which tells Rust Analyzer that that old text is no longer the latest one. Let's see how we handle notifications. So first of all, we have this notification dispatcher struct, which is a bit too smart Rust to allow us to basically say which type of notification it is and dispatch to it. In a nutshell, the notification is stored internally as untyped JSON value. We want to downcast this JSON value to a notification of particular type, like did open text document or work done progress, and then work with it. This visitor interface does it. It tries to downcast the current notification. It checks that the current notification has the method which corresponds to the current notification type, and then it tries to downcast it, using this extract method, which does this serda from value. And if we actually manage to extract this, we run the callback. And if we didn't, we go to the next handler. So let's look at this documentation, this notification. Did open text document. This is sent by the editor to the server once a user opens a new text document. This means that from now on, you shouldn't trust the contents of a document on the disk. You should trust what the editor tells to you. So in this case, we add this document to the in-memory documentation collection, and we set the contents of this document to what the editor told us. Because if we see at the parameters of this documentation, yes, it holds text document item, which holds the path of this document and also holds the current text of this document. After the did open text document notification, the client usually sends a bunch of did change text document notification, which can these notifications contain a diff to the current state of a file, and here we take the old contents of a file, and then we apply this diff using some fancy algorithm. Well, not really fancy, but pretty fiddly. And then we set the new file contents to this document. And finally, did close undoes the did open notification. We remove the document from the collection of in-memory documents, and we do something about diagnostics here. There is a bunch of notifications about anything else, but they're not, well, they're important, but we won't be covering here. Specifically, this one, again, this is about dynamic configuration changes, which is hard. Okay, so what I want to tell you now is one thing where this Dart protocol, in my opinion, is better than LSP, is handling of these kind of changes. So, if you recall, I've told you that the difference between notification and request and in JSON RPC protocol is that you don't get a response to a notification. And notice how text documents changes are notifications. This is a bit of a suboptimal decision. Why? Imagine you're an LSP client and you send a did change text document to the server. After you've sent this document, this change, you get some request from a server or some diagnostics or something like that. And that diagnostics mentions the document you've just sent the changes for. The question is, was this diagnostic produced before the server acknowledged the change or after? Because the client didn't get a response to the did change notification, it doesn't know. In other words, it's impossible for the client to know the state of the world on the server. It can kind of like hope that the server will be eventually consistent and that the eventual set of the diagnostics will correspond to the current state on the server. However, because it doesn't know for each specific diagnostic set which state of the world it corresponds to, it cannot tell if the current set of diagnostics is the freshest one or if there are any updates. LSP protocol has some hacks to work around it. Specifically, it sends versions together with documents, and document versions help you if you are talking about the single document. But it might be the case that interactions between two different text files are still missed. For example, you might be editing a file A, and that actually changes the set of diagnostics or highlighting or anything else in file B. And if the editor sends a change notification for file A, and then get some kind of data from the server about file B. The client knows the version of the B file, which the server used while computing that information, but it doesn't know the version of the A file. And yeah, that might affect the correctness of results. The Dart protocol doesn't have this issue. In the Dart protocol, changes are always acknowledged. So in the Dart protocol, you notify the server that file changed. And then if you get acknowledgement of a change before the diagnostics, you know the diagnostics actually contain the change. If you get the diagnostics first and acknowledgement second, then you know the diagnostics were computed before it changed. Anyway, that's like, to clarify, I do believe that the Dart solution is better here, but this is absolutely not something which actually affects the real user experience. It is about correctness in the edge cases. For the common case, Rust LISA protocol, LSP protocol is perfectly fine, and you actually don't hit this in practice. It is just that some like theoretical property that the system doesn't have. Anyway, this is how notifications handled, and most notifications actually update the state of the Rust analyzer. So the handling of notifications, like a flow of data during notification, is pretty simple to the flow of data during VFS modification. The next interesting thing we will be looking at are requests. So let's track how something like syntax highlighting goes through Rust analyzer. So first, syntax highlighting request is received via this inbox. And then we go to this case. And then we go to the onRequest function. Here, we should find, yeah, there's a whole bunch of stuff which happens here. Okay, yeah. Here, the semantic highlighting request goes to this handle. We will be looking at the actual handling function in a second. But first, let's look how this on method works, because for requests, on method works slightly differently. And yes, that's actually an interesting difference. So when we were handling notifications, because notifications update the state, we were handling them on the main loop. For requests, we generally want to handle them off the main loop, on the background thread. However, some requests are really high priority. They need to be handled as fast as possible. And for those requests, we have onSync method, which handles requests on the main loop. For example, Rust Analyzer has this join lines method, not the method functionality, that when you have like something like this and you press join lines, Rust Analyzer smartly removes braces and does other cool stuff. As this is related to typing, basically the user can't type further until this request is completed. It is really imperative that this join lines request doesn't wait for some idle thread in the main loop. It is really imperative that it is handled immediately, and that's why it goes via sync method. The on method, which we use for most of the requests, spawns the job on the background. Specifically, we take this task pool and spawn a task. The task calls the handler we have. So this F here is this function, handle semantic tokens full. It returns us some kind of a response. We then construct the response object, task response, and it will get sent to the sender which we have in the main loop, in the global state. So I guess I need handle. No, I get next event. So task pool receiver, which we select here, is exactly where this task response will go to. Okay. So let's for a moment ignore the actual handling function and let's look at how this request will be completed. So we get a response from some background task, and we just send this response to the sender with LSP messages. Again, requests and responses need to be paired using IDs. So we use this request queue data structure to find out the original request, this response or respond to, and also to compute some statistics about this request, like how long did it took. Okay, so that's the flow of requests. We get request from the LSP server. We run it through dispatcher, which determines which kind of request it is. And if it is a background request, which is the typical case, it gets found onto a thread pool. It is then executed on the thread pool, and it constructs a response object. This response object is shuffled back to the main loop, and then it is sent from the main loop to the LSP server. An interesting point. It actually would be possible to send this response directly to the LSP client, not to shuffle it through the main loop one more time, but I find it cleaner if all the reading and writing actually goes through the main loop, because then you get this nice property that there is a single place in the whole code base, like this line, where you can inspect everything which happens, instead of this request and response logic being spread throughout the code base. Okay, so let's peek a little bit into how the request is actually handled. First of all, global state exists only on the main loop, but the snapshot returns global state snapshot. And this is a read-only thing which you can use from handlers. The core thing which happens here is that we convert analysis host into analysis. And the other thing are kind of like not really needed for most of the requests. We move this snapshot to another thread. This closure will be executed on a different thread. Here, first of all, we install a panic context. If Rust analyzer panics, you can go to the logs. Actually wonder if Rust analyzer have been panicking during this session. No, there weren't any kind of panics. Yeah. So if Rust analyzer panics, you will see a panic message here, and the panic message would actually contain the specific LSP request, which caused Rust analyzer to panic, which is really helpful for debugging. And in the handlers, we will use the analysis in the snapshot to call a method which returns as a plain old data describing highlighting. And again, reminder, everything is cancelable. So this can actually return with error canceled, which then will be computed to which will be converted to an error, and the result to response function will handle this is cancelled case specially, and will craft a response which wouldn't which will cause the client to not treat this as a real error. Which basically, if the client sends something like syntax highlighting, and then it sends a notification which changes some file, then syntax highlighting results become obsolete, and we respond saying, hey, the syntax highlighting you asked, it is no longer valid. So if you still care about this, please resend the highlighting request. Okay. Yep, so we compute highlighting, and then we compute highlighting, convert highlighting to LSP representation. This two proto module is one of my most favorite in Rust Analyzer. It is pretty big, but it's also stupidly simple. And the only thing it does is that it converts from types in the IDE crates to specific JSON types of the LSP protocol. And the reason I like it is because, as I've said, Rust Analyzer has a lot of facades to make changing things easier. And this is one of such facades which isolates the internal representation of Rust Analyzer from details of language server protocol. So we can make the internal representation as rich and as featureful as we want, and then there is a single place where we need to dump it down to what LSP supports in the two proto file. Okay, so we convert this to the LSP representation, update the caches, which actually is like a really unusual operation. Typically, there are no extra caches. And then we return a response, which we get in the main loop and respond to the client. And actually, I think that's roughly how it looks like. Again, to recap, Rust Analyzer is basically a giant event loop. Well, not a giant event loop, a really, really, really tiny event loop. This is what Rust Analyzer is. This event loop manages state. The state is really creatively called GlobalState. This loop has unique, exclusive access to the state. This loop processes several kinds of events. The three most important sources are the messages from the LSP protocol, messages from the virtual file system, and also the results of the background tasks. When processing a message, if this is notification from a protocol or a virtual file system change, something which affects the state of the loop, the main loop applies this change in place. And several consecutive changes are batched. If at the start of the main loop we get 10 changes from a file system, we apply all 10 changes in the row. After we applied the currently available batch of changes, we look at the accumulated changelog, apply this changelog to the underlying analysis host, and then we resend the diagnostics and repeat. When the event is not a request for change, but rather a request like a go to definition or syntax highlighting or extend selection or something like that, we create a snapshot of the global state, send the snapshot to a thread pool, compute the results on the thread pool, and send the results back to the main loop. If the main loop gets a result from the background task, it sends this result to the client. Finally, if it so happens that some request is being handled on the thread pool, and at the same time a new request, a new notification for change comes in, then using the cancellation mechanism we described last time, the background work is actually cancelled, and then the change is applied in place. If the request gets cancelled, we still answer to the client that the request was cancelled. It's just that we use a dummy response that, hey, no information, please re-ask if you still care about this. And that's, I think, basically it. If we ignore the horribly complicated bit about configuration being updated dynamically. Okay, I guess that's it for now. Thank you for listening. Bye.